Okay, let's unpack this. Our sources today are pretty technical. Diving deep into quantum mechanics, we're focusing on something called a polariton. It sounds a bit out there, half light, half matter. Our mission, though, is simple. Pull out the key info about this. Well, this quasi-particle. It seems it could really change things in energy and computing.
Right. So the textbook definition, a polariton is a bosonic quasi-particle. But okay, let's break that down. A quasi-particle, it acts like a particle, but it's really an excitation across the whole system, you know. And the polariton happens when light, a photon, gets, well, strongly coupled, really tangled up with some excitation in the material. Think an exciton or maybe a phonon.
That's quite a concept. Why the emphasis on it being bosonic? Is that important right off the bat? Does that tell us something about what it can do?
Oh, absolutely. Crucial point. See, bosons, they're the sociable ones in the quantum world. They can all pile into the same state. That's fundamental for things like lasers or superfluids. It makes the polariton very different from, say, a polaron.
Ah, okay, I saw that term too. Polaron. Sounds similar.
Yeah, easy to mix up. But a polaron is fermionic, basically an electron dragging a distortion around with it. Totally different behavior. We're focused on this light-matter hybrid boson.
Got it. So this strong coupling, that's the magic ingredient here. If light waves and these material oscillations are usually separate things, how does physics sort of force them together?
It's because the polariton state becomes the new stable configuration, the new normal mode for the system under those conditions. It's a direct result of something called level repulsion. You might also hear it called the avoided crossing principle.
Level repulsion. Avoided crossing. Can you give us a picture of that?
Sure. Imagine you have two energy levels, one for the light, one for the matter excitation. As you tune the system, these levels approach each other. But if they can interact strongly, they sort of push each other away instead of crossing. They repel. And in doing so, they mix, creating two new hybrid states, the polariton. They avoid crossing paths. Ah, okay. Like they're forced onto new tracks entirely. So what's the real world effect? What happens to light inside a crystal when this strong coupling takes over?
Well, the main thing is polaritons mean you're violating the weak coupling limit. The light isn't free anymore. Its photons don't just zip through the material unchanged. And critically, how fast they do move depends very, very strongly on the photon's frequency.
So you get a handle, a way to control light speed within the material just by tuning the frequency.
Exactly. It gives you this fantastic tunable control over light propagation.
That's the physics now. But you mentioned this isn't brand new, this idea of light and matter merging. It's been around.
Oh, yeah. The underlying concepts, they go back quite a way. Oscillations linked to this were actually seen in ionized gases way back in 1929 by Tonks and Langmuir.
Huh.
But the theory for this kind of polariton in solids, Kirill Borisovich Tolpigo did key theoretical work. And initially, folks like Salman Pekar in the Soviet Union called them light excitons. Makes sense, right?
It does, yeah. Light plus exciton. So why polariton? Well, the name polariton was suggested later by John Hopfield, and it kind of stuck internationally. It emphasizes the link to the material's dielectric polarization.
And it's not just one kind of polariton, is it? The sources mention different types depending on what the light couples to.
Precisely. You mentioned excitons and phonons earlier. So if you couple infrared light with an optical phonon, that lattice vibration, you get phonon polaritons. Couple visible light with an exciton, that electron hole pair, you get exciton polaritons. Different light, different matter excitation, different polariton.
Which means you can tailor these things across different energy ranges, different light colors.
That's the beauty of it. You can potentially engineer these light-matter hybrids across, well, much of the electromagnetic spectrum.
Okay, let's connect this to the bigger picture. Where is this heading now? I saw a mention of a big discovery in 2016.
Ah, yes, the room temperature superfluidity observation. That was a major milestone.
Superfluidity, meaning flow without resistance, like superconductors, but different. And at room temperature, why is that such a big deal?
Exactly. Frictionless flow. Doing that without needing extreme cold, liquid helium temperatures, that just blows the doors open for potential applications. Think lossless energy flow, maybe ultra-efficient circuits that don't need cryogenics.
Wow. And there was more recent buzz too, right? Something about quantum tech?
Yes, in 2018, there was a report about creating a novel 3-photon form of light. Polaritons were thought to be involved. That could be a pathway towards new types of quantum bits or logic gates for quantum computers.
Okay, quantum computing, superfluidity.
Yeah.
And the latest I saw was 2024, something very practical with solar cells and LEDs.
That's right. Really interesting work. Researchers used a specific setup, polaritons formed in a thin 2D layer of a perovskite material.
Perovskites, okay, those pop up in solar research a lot.
They do, and they put this layer inside a special optical cavity, a Fabry-Perot microcavity, to really enhance the light-matter interaction. The goal was to manage something called exciton annihilation. Basically, when two excitons meet, they can destroy each other, wasting energy.
Ah, so they lose energy that could have been light or electricity.
Exactly. But by forcing the excitons into the polariton state, they could suppress this annihilation process.
And the result.
They showed it could significantly boost the efficiency of potential solar cells and also increase the brightness, the intensity you could get from LEDs based on this material.
So if we pull all this together,
Hmm.
what's the main takeaway?
I think if we connect this to the bigger picture, polaritons are fundamentally a powerful new tool. They let us engineer, really design how light and matter talk to each other at the most basic level. We're getting new ways to control material properties that we used to think were just fixed.
So what does this all mean for you listening in?
Well, it means keeping an eye on this emerging field people are calling it polaritonics, the potential for a whole new class of devices, maybe things like a super efficient compact polariton laser, or harnessing that room temperature polariton superfluid. It seems much closer than it used to be. Definitely something to watch.